so I think we should get started.
Okay.
So we have our third lecture by Kantaro, and this is the final lecture. Then tomorrow morning we have another, just as a reminder, we have another discussion session as a time zone catch up. And then tomorrow we have a talk by Nathalie Paquette, followed by the Gongsho and poster session. And we'll announce that tomorrow after the talk. Okay, so Kantaro, please. And everyone, please ask questions.
Yeah, sure. So let's start. I don't know. Okay, I try. Somehow my PDF viewer is something like. But I try anything anyway. So this is the lecture 3. I changed a bit the plan. So obviously I cannot do everything I've done before starting the lecture. So yeah, today I will first talk about the one-form symmetry in the Maxwell theory, just for the, this is for the Maxwell theory. And then I will talk about the 60 anomaly in the 60 supercommon field theory, because I guess that the next week the Fabio and Ivan both will talk about those. So it's good to know that at least how to compute the anomaly in this case. And yeah, and so yeah, I failed to mention yesterday that I just found Monday night that there is a good review covering the not this one, but about it's also related to the 60 CFTs, but also good review on by the Samuel Monnier, and so if you're interested, you should look at it. Okay, so let's start. So first I talk about the one-form symmetry in the Maxwell theory, for the Maxwell theory, and so this is in the original paper of the higher form symmetry by the guy Otto Kapuskin that worked with. So the Maxwell theory is just I don't know why I keep this. So it's just a free theory. The action is just f star s. The equation of motion is the equals to 0, and you also have Bianchi identity because f is dA, so the f equals to 0. And those two equations are called the Maxwell equation, if you know. And okay, so the point is that these two equations are just d of something equals to 0. You can regard these as the conservation law. So if I just define up to some normalization constant, define, roughly speaking, you can define the two currents, which is just mu sigma. Mu sigma f. So like this, then automatically these two equations, the Maxwell equations, says that these two, I just redefined the letters, and it just regarded as the conservation law of these currents. Okay, so but unlike the usual current operators, these two have the two indices. Each have two indices and the anticommute. Okay, so this obviously by the anticommuting indices. So such such a phenomena is dubbed as the U1 one-form symmetry by these also scarlet capacity level of it. So one-form symmetry kinds. Okay, and so and these are supposed to be some generalization of some symmetry. So we want to find some charged object, and those charged objects are the Wilson line and 't Hooft line for the so this E stands for the electric and N stands for the magnetic. And so for U1E one-form symmetry, it's the charged object is the Wilson line. Wilson line is just okay. Integral of A, and for the magnetic symmetry, it's a 't Hooft line, which is a dual, the electromagnetic dual of the Wilson line, or you can think it as the Wald line of the probe magnetic object. Okay. So, and also you can think about the background for those one-form symmetries. So backgrounds are, I call it B, E, and BM. Those are the locally two forms. To be precise, globally, it's something called jugs, but I don't get into the detail. And and you can couple the system to the background, and let's just write them. Okay, so yeah, so for the usual case, you write a J is the zero-form symmetry is the J. The current operator have a single index, and the corresponding background have also a single index, and you contract. Here you have the two indices anti-commute, so you also prepare the background to have the two indices that anti-commute, which is a two-form, and you contract with the current operator. So that's the definition of the background. One-form symmetric background.
There's a question in the chat.
Yes. So whenever a Lagrangian formulation exists, is it always possible to compute the conserved currents via the Noether theorem, as in this case, or there can be some abstractions? So I guess so. For the continuous symmetry in particular, yes. If you know that, but yeah, for the zero form symmetry, yes. If you know how also if you know how the symmetry acts on this field in the Lagrangian, yeah. But might miss magnetic currents. Sorry, let me check. I thought I wrote things correct, but maybe I made some stupid mistake. Please, I don't get the.
I think Jonathan just means that if you use that method, you might miss the magnetic currents. It's not in your note, but as a response to the answer to the question.
Yes, that's possible. So yeah, thanks. And yeah, I mean, listing all the symmetries is not necessarily an easy task. Even you have a Lagrangian theory, so you might miss something. Even if you have some Lagrangian formulation. Yes, I think so. Yes. Yeah. All this means that you have to be very, very careful. Okay, so yeah, and this is a background, and so the natural extension of the usual gauge transformation to the zero form symmetry background is that the this. So okay, so here these capital lambdas are one form. Okay, so this have the one index already, and yeah, I mean, if you want to write it in the with the index notation, then I mean the gauge parameter have the one index. That's why it is called the one form symmetry. The parameter gauge transformation parameter is the one form. That's why they call it the one form symmetry. And so just the gauge transformation law is this. So this is the natural generalization of the gauge transformation law of the zero form symmetry background. Okay. And so the Maxwell theory have two U1 one form symmetries in this sense, and these two one form symmetries have mixed anomaly. Okay. So well, I should read more. Yes. Let me just here. So so to see that the fixed anomaly, you look at the 2-point function of these two current operators. Okay, and hit with the derivative on one of the indices. So if you do this and compute say Lorentz gauge, you can choose any gauge. But here specifically, if you choose the Lorentz gauge, what do you get is, so this is free theory. This is just pick the free propagator. Okay, so this is just the F to F. So you just pre-propagate and hitting with the derivatives, and you will find that if there's a contact term with these two, like the derivative of the delta function. So in other words, if we consider it like this, so this is the background coupling. If it's visualized on the background coupling to magnetic background, and if you compute the conservation law of the elliptic one form symmetry, then from the one expanding the background, and from the first order in B, we get the sigma alpha and B. And just doing the of X, okay, because you have the delta function. Okay, so this is the modified. I mean, this is a modified conservation law of this one form symmetry under the presence of the magnetic one form symmetry background. So if we like define the two form current operator JE by this, so then this equation I rewrite this just modified conservation law is this. Okay. Here I'm very sloppy about every coefficient. And okay, so on the other hand, if you hit the derivative with the indices in rho, then it is still conserved. So even so the conservation law for the magnetic one-hole symmetry is not modified. So this still depends on the gauge choice or your other choice of the computation. Yeah, so this result doesn't look like the electromagnetic invariant, but this is just because we picked the Lorentz gauge to some particular gauge. And so what's invariant is the Hooft anomaly, and to detect that, I mean anomaly polynomial, and to detect that, so we have if we couple with the both background, we have these terms. And so if you do the gauge transformation for the B's, we have these terms. And just do the integration by parts, we get the dj wedge lambda, but we set that the dj equals to dbm. So here, so this is the db magnetic wedge lambda e. And so this is the anomalous phase. And this anomalous phase can be obtained by inflow. So if you consider the five-dimensional invertible QFT with the term look just like this. Okay. Then if you do the gauge transformation, you get the d lambda e, and do the integration by parts. You get, so here of course the n5 is such that if its boundary is your space-time manifold. Okay, and you can go further hit with the formal D. You get the anomaly polynomial, which is okay. So this is the anomaly polynomial. So it means that there's a mixed anomaly between the electric one-form symmetry and magnetic one-form symmetry. Okay, so this is just about the free theory, and I wanted to talk about the non-abelian interacting Young mills, but it seems like the time doesn't permit me to do so. And so here I just briefly mentioned what happens in the non-abelian case. So if you consider some general G Young mills theory, so you still might have one-form symmetries, and the one-form symmetries are this. So elliptic one-form symmetry is valued in the center. This is center of your gauge group. So the charged object is also again the Wilson line. And so there's no so in general, so G is no abelian. This center is discrete. For SUN, of course, it's the n. So we don't have a current operator. Yeah. So it's more subtle to describe it, but there is. Okay. So and the magnetic, there can also be a magnetic symmetry if it's not simply connected. And So yeah. So this is the fundamental group. And also, if the both two of them exist, like SO group, SO even. So for SO even, both the center is non-trivial and the pi one is non-trivial. So there also the electric and magnetic symmetry. And yeah, so in the very recent paper by Potion Shi and Hotatsu, described that, considered that such case, and there is a very analogous mixed anomaly in the case. So although those are discrete, so for SO case it's both Z2, SO even for the electric and magnetic one-hot symmetries are Z2, and there's the mixed anomaly. Okay. And also, yeah, I think if you consider some SU4 mod, yeah, that's SO6, but SU and modulo some ZK, K divides N, then you can have both electric and magnetic symmetry, and there can be mixed anomaly. Okay, so one very important paper is this, Gaiotto, Kapustin, Komárkovszky, Cyber. And so in their paper, they considered SU and Yang-Mills. So in that case, the only the center is not trivial, so you only have the electric one. But still, it can have mixed anomaly with other possibly zero form symmetry. And in their paper, they considered the time reversal for the CP symmetry, which is discrete space-time symmetry. So the CP exists only when the theta angle is 0 or pi, and theta angle equals to 0 is boring. But when you tune theta angle equals to pi, so the CP sends the theta to minus theta, but the theta is 2-pi periodic. Yeah, of course, this theta is yeah, for sure. I just write the theta term. Theta is the coefficient in front of the trace FHF topological term, and so this is 2-pi periodic because the instanton number is quantized, and so the CP sends theta to minus theta, but theta equals to theta, because theta is 2-pi periodic. Theta equals to pi is the is preserved by CP naively, but what they found is that there is a mixed anomaly between the CP and this ZN one symmetry. And the reason why is that this, once you turn on the ZN one form symmetry background, then it's like the 't Hooft twisted boundary condition, if you know it. So the quantization condition of the instanton number changes, and there can be, so this is basically because the fractional instanton under the presence of the one-form symmetry background, and so once the D is turned on, then the theta is no longer 2-pi periodic. So then CP acts on the theory in non-trivial way. So that's the mixed anomaly, and so it was surprising that this doesn't have any fermion. So yeah. So our old intuition is that the anomaly typically comes from fermions, and it is still true, but you can also find some anomaly from purely bosonic system. This is an example, and this anomaly sets under some likely assumptions. This anomaly implies that the CP is broken at the theta equals pi, for theta equals pi, and the temperature at the zero temperature, and also if you turn on the temperatures, so corresponding to the circular compactification, so the temperature where the CP is restored should be above the temperature of the deconfinement transition under some assumptions on top of the anomalies. But yes, so those were the predictions, and it's somewhat surprising that you can't say anything about the phase transition of this pure Yang theory from some just analytic or the topological viewpoint. So it was very surprising, and of course this stimulates many works. So many people consider, say, QCD in 4D, 3D, and others, and so it's still a very hot area of the research. Okay, so this was it about the Yang mills. Any questions?
Yeah, so how does this mixed anomaly imply that CP is broken at theta equals pi? I mean, I understand that you're saying it's likely, but why
I said, so you can still say some, of course here I assume the confinement. So yeah, so mixed anomaly means that the theory in IR cannot be trivial, and the easy way to saturate this mixed anomaly in IR is to break one of the symmetry. So either the CP is broken or the long haul symmetry is broken, but yeah.
I see. Secondly, in the Maxwell theory, if we were to try to gauge the one-form magnetic symmetry,
yeah.
Does the resultant theory have any dynamics?
So it's like if you want to gauge entire magnetic symmetry,
yeah,
that's like you are right, and I think you're going to get some R. Yeah, I'm a bit afraid to say this. If you gauge some subgroups, then if you gauge subgroups, the GN subgroup of U1, that amounts to change the radius of U1. So after gauging, you so, but if you try to gauge the whole thing, that means okay. So and that's you are going to get a dynamical two-form field, which is dual in 4D, which is dual to the periodic scalar. So the resulting system is like the periodic scalar coupled to U1 by shift action.
I see.
Yeah, that's what you get.
Thank you.
Any other questions?
So is it also possible that instead of having conserved magnetic current, we could have conserved electric current, maybe by choosing a different
different counter term. Yes, yeah. I haven't done that, but probably maybe if you do the arc gauge, you can move one to the other. I haven't done that computation.
Okay.
Maybe fun.
Yeah. Thank you.
Okay, so I move on to the 60. Okay, and yeah, so yeah, before talking about the 60 SCFT, I have to the anomaly for the 60 SCFT. I have to introduce some basic notions on the topic. So in higher dimensions, I mean 5D and 60, or higher even, then the gauge coupling is non-renormalizable. So naively, you don't expect that in UV you can find some well-defined gauge theory. Well-defined UV in some gauge theory in higher than 4 dimensions. However, I mean, that's what you're told when you're working on the 4D, and if you have too many matter fields, fermions, let's say, then I mean, if you have too many, then it's not asymptotic free, and the end of the story. But so yeah, in 5D or higher, then yeah, no matter what, even pure gauge theory is non-renormalizable coupling. However, there are string theory or M theory or F theory constructions of those such gauge theories, and you can I mean in these dimensions 5D and 60, you can take the decoupling limit from the gravity. Okay, and and those constructions, as far as I understand, is reliable only when there is a Suzy. So I assume the supersymmetry. And yeah, I'm sure the Fabio is going to talk more about this. Yeah. But here I'm just saying that there is a construction from the string theory. You will learn from Fabio how to do that. Okay, so and also these constructions predicts that there is, in many cases, not all, in many cases, there is a UV fixed point. Okay, which is totally non-obvious from the field theory point of view, that you have UV fixed point. It's very coming from top down, from the string theory or MOS theory. Okay, so you have some mysterious UV fixed point which is strongly coupled, predicted by the string theory, and the string theory also predicts a flow from the UV fixed point to the weakly coupled effective field theory in IR. Okay? And this flow is triggered by, in 5D, typically it is mass parameter. And yeah, so well, this is strongly coupled. So it's not, there's no longer Lagrangian direct in UV, but there's some here. Mass means that a particular operator in particular representation of superconformal groups. And in 60, such flow is triggered by some depth to some scale operator. Okay. And here I'm going to talk about the 60. Okay, so in 60, because it's the even dimensions, we can talk about the non-trivial anomaly polynomial. So one question we can have is that so how to compute the anomaly polynomial, and so because we have the first anomaly matching, so naively we can do that by computing the anomaly polynomial in the effective field theory, and that should match with the UV fixed point. Okay, but yeah, but we have to include the some particular topological effect in the effective field theory, as we are going to see. Okay, and so this is here although I talked about the non-partitive anomaly in the previous lectures, but here I only talk about the partitive anomaly, and for the non-partitive anomaly, I think there is no general understanding for the general 6D CFTs or 5D. But so one place to look at is here. Another is, well, I thought, and also, yes, okay, I failed to write it. Also, there's more previous works by Samuel Monnier. I don't want to misspell him. He has more earlier works on the partitive part, a non-partitive part, but here I cannot cover it, or nor I understand it. Okay, so before talking more about that, I have to briefly introduce the 60 supermultiplets. So the 60 is, here I consider the minimal amount of the supersymmetry, which is 1, 0. And there are 3 masses multiplet with the spin less than or equal to 1. And so 1 is a tensor. Okay, so start from the familiar one. So for you have vector multiplets. In 60, you have just gauge field and gauge genome, and you do not have scalar in vector multiplet in 60. Okay, in hyper is as usual. You have some fermion and scalar, and this I is some SU2R. So n equals to 1, 0 have SU2R symmetry, and this I is the SU2R index, and this plus and minus are the chirality and 60 chirality. Okay. So there's one unfamiliar multiplet in 60, 1, 0 series, which is a tensor multiplet. So consists of so A is real scalar, Xi is fermion, and B is a two-form field. This is antisymmetric, but it is also a self-dual. Means that whose field strength H equals to dB, H equals to star H. Okay. Self-dual means that we restrict the field to satisfy this equation, and this equation is meaningful in Lorentzian and in 60. So one problem or like difficulty in this self-dual two-form field is that actually there's no easy Lagrangian formulation. there are hard Lagrangian formations, but there is no easy Lagrangian formation because neither you would write for this dynamical two-form field, use like the H wedge star H is the kinetic term. However, if you impose H equals to star H, it's self-dual. If you impose a self-dual condition, this is 0. H wedge H, but H is free form, so it's 0. So, but yeah. So here but still it exists in a non-trivial theory. So one way to describe this theory is using some non-polynomial Lagrangian that's called the PSD action. Another is, but a more natural way is described, say, in this paper or more earlier paper by Beroff and Muller, that is to describe this self-dual two-form field as a boundary theory of the 7D QFT. So yeah, so here I just say that there is some way to describe it, and still EOM we can still easily talk about the classical theory. So classical theory is EOM is still this, and this is all equals to the Bianchi identity of H because of the self-duality. Okay, and so this was the self-dual. This plus means it's self-dual, and yeah. Okay, so these are the possible 60 Wakamakizhe super multiplets, and so here to compute the anomaly polynomial, we consider the tensor branch effective field theory, which means that so the UV fixed point is strongly coupled. So it's mysterious, but we assume that if we turn on the some particular kind of branch web, then it flows to the effective field theory, described by weakly coupled effective field theory, described by these composed of these three types of multiplets. So it can contain many or some number of the tensor multiplet. Also can have some gauge group, which can be some product, and also it can contain some hypermultiplet charged under this gauge group. Okay, so in particular, I assume the EFT Lagrangian. Of course, we should have some Yang-Mills term for some case gauge group. Okay, but the gauge coupling, I assume the gauge coupling is controlled by the depth of the real scalar in the tensor branch multiplet. So that's one assumption on this EFT. So the gauge coupling squared is the web of the so I don't have to say it. Yes. So the gauge coupling is controlled by the depth of the tensor branch, and I assume that if you go backwards to the UV, UV corresponds to the origin of the this backend moduli. So there the gauge coupling blows up. Okay, so we are assuming that starting from some EFT and tune the wave to be 0, where it becomes very strongly coupled. There is a UV fixed point, which is far from obvious. I mean, from the field theory point of view, I again emphasize there's no reason to believe such thing, but string theory and series theory implies that is the case. Okay, and so these are some assumptions of the topic. So here, of course, we have gauge group. So, and this is 60. So we should care about the gauge anomaly cancellation. Okay. So if the gauge anomaly is cancelled, can we compute the anomaly polynomial in UV? And to address these two questions, the 60 version of Green-Schwarz mechanism, which I'm going to describe, is very important. Here, I mean, the Green-Schwarz mechanism is, of course, introduced to the 10D heterotic string by Green and Schwarz, original paper. And so here, the very similar phenomena happens in 60. Okay. So anomaly, in this page, I just recorded the anomaly polynomial for the free multiplets. In this, oh yeah. Oh, for the anomaly polynomial for the 60 CFTs, these are there's a work done by me, but also earlier work by Ken. So these two are the original papers. And so the rest of that paper page is just I recorded the anomaly polynomial for the free supermultiplets. And so for tensor multiplet, you have to include the contribution from the self-dual tensor. And so, yeah, because it's chiral, so although it's not a fermion, but chiral, there is a kind of anomaly. I mean, even for the perturbative anomaly. And so it's done by, you can try to do, in a sense, do the one loop computation. But you can also derive it in the modern point of view. So one place you can look at is the modern point of view. I mean, they do the similar thing of the Yeta invariant for the fermion. So there I describe the chiral fermion as some zero mode living in the other domain wall of the higher dimensional theory. So you can or the boundary of higher dimensional invertible QFT, and so there's also, you can write down the invertible QFT in 7D such that the chiral self-dual tensor naturally is on its boundary. And yeah, so you can look at this recent paper. This is not original. I think original paper is the Beroff and Muir, and yeah, I read it. And you can, yeah, so you can look at either. But about the computation of anomaly, I think you should look at it's good to look at the recent paper by Chance, Yuji, Kazuya. Okay, so anyway, these are the I just recorded. So here C2R is some essentially trace of the field strength for the SC2R background. So this so C2R is some chunk class for the SC2R background, and other F. So these are the gauge. Yeah, go somewhere. Yeah, F is a gauge field strength. Okay. And yeah, like this DG is just the dimension of the group, and 0 is the dimension of the representation. I just recorded, and so okay, so given some, yeah. So what we do is that assume some spectrum of the EFT. So we have some number of tensors, some gauge groups, and the representations. And so then we substitute here, and we get the naive contribution on naive anomaly polynomial. And we want to cancel the gauge anomaly. So we need to so the set of the G and rho satisfy that so the pure gauge anomalies in this anomaly polynomials are like the trace F to the fourth, and also the trace F. Here I mean trace. Oh yeah, it doesn't appear, but if you expand, say, this one, you also get it. Say if it rho is fundamental, you also get the trace adjoint. If you rewrite it as adjoint, you can write you're going to have like this, the trace F squared. So you have so pure gauge anomaly looks like these two, and these two should vanish. And also, if you assume that UV is SCFT, the fixed point, then I think the recent result by Cordova, Dimitrescu, Intrigator, I think this is not published yet. It's not published yet. Please correct me if it's not true. But anyway, they claim that if in this superconformal field theory, there cannot be no mixed gauge and gravity or SC2R anomaly. So the mixed gauge and gravity anomaly is like this. So this is SC2R. This is the gauge. So this term is the mixed anomaly. And yeah. So yeah, in the original paper, we just assumed that this condition, but it's proven by some representation theory of the superconformal group by these gentlemen. And so if we assume this stronger condition, that not just a pure gauge, but we also demand that there's no gravitation and SC2R anomaly, then there's no solution such that the G and rho such that all the anomaly involving this background is 0. There's no solution. And so if you allow the mixed gauge and gravity anomaly, then it cannot be the fixed point. UV cannot be fixed point, but still something more mysterious called the little string theory. And then then there's some more interesting story, but I don't have time to talk about it. Okay, so it seems that there's no solution naively to have a UV SCFT, but as I said, as I'm emphasizing, there is a construction from the string theory, M theory, F theory. So we made some mistake on the conclusion, and so what saves us is the 60 version of Green-Schwarz mechanism. Okay, so the point is that so we have the dynamical two-form field. So similarly to the Maxwell theory, because we have a one-form dynamical two-form field, we have U1 two-form symmetry. So the current of now 3 indices, and it's just essentially the field strength of B. Okay. And because of the self-duality, relating this H and star H, in this case we only have one U1 two-form symmetry, namely the electric symmetry is identified as magnetic symmetry. Okay, and okay, so if you write the background to the so this is two-form symmetry, so the background has to be locally three-form. Okay, and so formally it's like that. Although we don't have easy Lagrangian to describe it, but formally it's like that we write the H wedge C coupling. That's the coupling to the background. Okay, so then just the analogy to the Maxwell theory we've been talking, we expect that there is anomaly, so the anomaly polynomial is DC with DC. And actually, the contribution has to be divided by 2. This is hand wavy, but because this is a chiral, we picked half of this, so it's half. Okay, so after this hand wavy thing, we expect that we have an anomaly in this two-form U1 two-form symmetry. Okay, and so the way to save ourselves from the so we have to have some additional anomaly polynomial contribution to the anomaly that somehow cancels the gauge anomaly. Okay, so how can we get such thing? And the way is substitute into this background C with some Chern-Simon form composed of gauge field and also other backgrounds. I mean, some of the over some Chern-Simon terms. In other words, formally we write H wedge Chern-Simon term. Okay, so then, such coupling is called the Green-Schwarz coupling. Okay. And so in general, we have many tensor fields. We can have multiple tensor fields. So we can write the multiple such couplings. Okay, so then, so the Green-Schwartz contribution, contribution to the anomaly polynomial from this is, so if you have multiple tensor fields, the two-form symmetry anomaly polynomial looks like this. You have some matrix here. This is a kinetic matrix. So you have multiple tensor fields, so you can potentially have mixture. So that's a matrix. And okay, and so this is just, so this anomaly is when it's just treated as a general two-form symmetry background. But if we identify that background to be some other dynamical, possibly dynamical field, the chance-Simon term of it, then so we substitute it, and so the Simons. So we have some chance-Simon term, and okay. So if I write this to be some gauge invariant 4-form, yeah, of course this is chance-Simon is a chance-Simon 3-form, and so if I write the D of this chance-Simon term, which should define some gauge invariant 4-form field, then so the okay. There's additional contribution to from this kind of coupling. Okay, so if we write, roughly speaking, write this kind of topological coupling to the two-form field. So yeah, so to be explicit, this is like a trace F for the trace AF plus A cubed for the gauge field, and then you can get additional contribution. So we can use this to cancel the gauge anomaly, or mixed gauge and gravity gauge SU2 anomaly. So the total anomaly polynomial is just one loop contribution, which is just the sum of these naive contributions, and this Green-Schwartz contribution, which is just the square of 4-form. Okay, and so this one loop looks like that we have trace of a joint. If we move on, only use the trace of a joint, then like we have the trace F to the 4th potentially, and we have some. We can do the square compression to the left, so we can always write down like this. So, okay, K of C to R and some number and P1. Here the P1 is the gravity background, the Pontryagin class of the gravity, and yeah, I omit the global symmetry part. So, and K replaced by L. So here just I did the square completion with respect to the trace F squared for all the gauge groups. Okay, and so you can always do that, and then the rest, this piece is the rest. This does not contain the trace F squared. Yeah, here the trace is I only use trace of a joint. So then, okay. So this doesn't contain the gauge field strength. Okay, so the only problem is this part, because we cannot cancel this trace f to the fourth, which is not the square of something. So we cannot write it into square complete. So this is the only obstacle, and others can be treated if we tune the I4. If we take this part to be I4, basically, then we can always cancel it. Okay, so from the IR point of view, if this coefficient of this trace f to the fourth term vanishes for every gauge group, then at least this perturbative anomaly vanishes. So you just tune the I4 to cancel the second line, and then the result is the remainder term is the total anomaly polynomial. Okay. Yeah. Okay. So from the first anomaly matching, we expect that this total anomaly, it is the UV anomaly polynomial. Okay. So this is surprisingly cheap way to obtain some observable from that mysterious strongly coupled system. It's like that the theory is living on M5 brains, but we don't know a priori about anything about that. But once we know the IL tensor branch theory, then at least we can get one. Well, of course this is easiest one, but easiest observable in very cheap way by square completion, basically. Okay. So it's good. Okay, so this is just an example computation. So say the EFT is the gauge group is single SUK. Okay? And okay, so to cancel we have to cancel, tune the representation of the hypermultiplex such that the coefficient of trace f to the fourth term vanishes, and there are several choices. But the one choice is that the representation to be the 2K copies of fundamentals. Yeah, like the 4D superconformal 2CD. Okay, and so for this case, you can, and we also have one tensor multiplet to do the Green-Schwarz cancellation. We need the tensor multiplet to do the Green-Schwarz contribution. Okay, so then, oh yeah, these two are some relationship between the trace fundamental to f to the squared and f to the fourth to the trace of adjoint. So if you want to really compute, you need it. And okay, so here I just wrote the one loop contributions. I ignored the P1, ignored P1 and also the global symmetry. Just wrote the SU2R and the gauge field. So what to do is just square complete. So this is just a okay. So this is just sum over these three. Substitute the data of the spectrum, assumed spectrum. Okay, then what we do is just a square complete with respect to this. So square complete. Then let's use this. Okay. Okay, so here so we cancel, so this part is canceled by the Green-Schwarz coupling. We have H wedge Chern-Simons if we do the integration by parts. It looks like the B wedge I4 here. This I4 is this form up to some numerical constant. And okay, so this squared can be cancelled by the Green-Schwarz term. Then this is the total anomaly polynomial, and it should, if UV theory exists, then it should match with the anomaly polynomial for the UV theory. Okay, so I'm just saying the same thing again and again. Here I was thinking about the IR EFT, and like let's use K, there's 2K fundamental, 1 tensor, and Green-Schwarz coupling. Okay? And I probably Fabio will tell you that how to construct the UV SCFT from the string theory point of view. Okay. So we can. So we computed some anomaly polynomial for the assumed UV theory. You can formally take K equals to 1. So then this IR EFT, when it is K equals to 1, it's the 1 hypermultiplet. So SU1, the gauge group is gone, but still we have a 1 hyper and 1 tensor. And the two together hold the 2, 0. I mean, extended supersymmetry, 2, 0 tensor multiplet. And we still have the Green-Schwarz coupling coming from, because it involves the C2R, the background. So the Green-Schwarz, so if we just formally substitute K equals to 1, we still have the non-trivial coupling with the B with the background C2 field, background is C2R field strength. And okay, and in from the string theory or M theory point of view, also it predicts that the UV is also n equals to 2, 0 CFT. Okay, and this is very famous 2, 0 CFT on the 2 and 5 range in M theory. So yeah, maybe I should say this. So this for general K, this is a 2 and 5 range on proving the singularity of C2 mod VK. And when K equals to 1, there's no singularity. It's just the theory on M5 range. So this procedure is a bit formal because here you don't have any gauge group, so you don't need to have Green-Schwarz coupling, but yeah. But if you assume some kind of continuity in K, then this also computes the anomaly polynomial for the 2, 0 CFT, and it matches with the computation by other means, namely the anomaly inflow. Okay. So yeah, so you can just substitute K equals to 1 here, and you get the, I don't know, 11 over 12 something of the C2R squared. So that matches with the computation from M theory. You can directly compute the UV anomaly polynomial from the M theory point of view in this case, and it matches with it. Okay, so I just give you some exercise. So here I just consider one gauge group. You can think about the quiver. The EFT might be a quiver gauge theory. So you can consider this quiver that the n copies of SUK. Circle is the gauge, and this is flavor both sides. Okay, so the 60 version of the, if this were a 4D, this is conformal quiver. Okay, and just a 60 version, and also the tensors. So you also need the n tensor field to have the Green-Schwarz cancellation. Okay. So so this segment or line is the bifundamental between the gauge groups here. Okay, and so exercise is just to compute the anomaly polynomial. So assume that there's a UV and compute the anomaly polynomial, and by you just substitute the spectrum data to the anomaly one loop anomaly polynomial and the square complete, and take the remainder. Okay, so yeah, and then it's good to formally substitute k equals to 1, and the answer should be this. And this is some American equals to here n is n minus 1. When here, let me back up. So when there's single node, n has to be 2. So yeah, this is n minus 1. Okay. So when there's n minus 1 node, and if we formally substitute k equals to 1, then the answer should be this. And so this is the anomaly polynomial for the 2,0 theory, and on the n5 range. And so yeah, it's so you get somehow you get the cubes and cubes, and so yeah, so that comes from that when you just square complete. Yeah, and so this n cube dependence is peculiar thing to observe, because if this were not n5 but d brane, then you just, I mean, say if you're considering the d4 d3 brane something, then it's just you get the gauge theory. So the degrees of freedom depends on n squared. That's what happens for d branes. But for n5 brane, somehow it's n cubed, and so it's not the gauge theory in that sense. So, I mean, yeah, anomaly polynomial. You can think that anomaly polynomial very roughly counts the degrees of freedom. Okay. So then, so in a sense, the n5 branes have n cubed degrees of freedom, which means that it cannot be a conventional gauge theory, and it's strongly coupled something. Okay, so I will stop here and invite questions.
Okay, thank you very much for these super clear lectures. And let's all thank in our somewhat limited ways by clapping. So thanks very much. Questions? There were no questions in last hour, so there must be loads of them at this point. Please just unmute yourself or type it into the chat. Either works.
So is this the anomaly polynomial where the center of mass degree of freedom of the NM5 branes is still there? We haven't really decoupled.
Oh, good. I subtracted it. So if you do compute in this way, yeah. So yeah, to be consistent, yeah, the number of tensor fields has to be n minus 1.
Yeah.
So yeah, then the center of mass is subtracted. So this is without. Yeah, this is without center of mass. Thank you. Yes, of course, the center of mass contribution is just as written. So, but there's additional green shoots.
So, but there's also the statement that after removing the center of mass degree of freedom, we have a relative field theory, in the sense that we have a choice of partition function. After
You're right. Yeah, here I'm ignoring that fact, but you're right. When you remove the center of mass, so this 2,0 theory should be considered as the boundary theory of the dynamical 7D chance-animal theory. And yeah, so this anomaly polynomial captures, the non-invertible part. So there's also the invertible part. There's also non-invertible part, dynamical chance-animal theory in 7D. But of course, you can, on top of that, you can also have this counter term and in 7D. So this anomaly polynomial just captures that part.
And does it show a mixed 't Hooft anomaly between SU2R symmetry and the gauge? Sorry, the flavor.
Oh yeah, yes. Flavor group, yes. Yeah, I just didn't. Yeah, I just didn't write every term. This is just the C2R squared term. Yeah, I think there is. Yeah, mixed anomaly between the flavor group. Of course, when you take K equals to 1, there is no flavor. Yeah. Yeah.
Thank you.
Thank you. Any other questions?
No? Okay. So just a reminder, tomorrow morning we'll again have a question session, and then on Friday there'll be a discussion session together with Kantaro and other so-called discussants led by Ken, where we'll discuss various open questions that have sort of remained unanswered, but also perhaps future research directions in this particular topic. So I think we should thank Kantaro for these beautiful lectures once again.
Thank you. Okay. Thank you for listening.
Thanks very much. And we will resume with Irene's third lecture in about 20 minutes. Actually, less.